welcome to Basic Bit. Today is December 9th and we are on day 9. The problem today is called binary search tree iterator. So you can probably recall a couple days back we did a binary search tree problem where we converted a binary search tree into an ordered search tree. And one property I mentioned at the time is that when you traverse a binary search tree in order, you get the values ordered from least to greatest. This problem is asking us to do a variation of in-order traversal. We need to implement two functions. The first function is hasNext, which should return true if there's any numbers left in the traversal. And the second function that we need to implement is next, which should return the value of the next node in the in-order traversal. So in the init function, we can do self.list is equal to in-order traversal of the root. Okay, and let's implement that in-order traversal as a helper function. So if not node, we want to return an empty list. Else, we want to return, we first recursively call the left subtree, and then we join that with the value at the current node, and we recursively call in-order traversal on the right subtree. And so we can create also a pointer that points to, we're going to initialize it at -1. So every time next is called, I'm going to increment the pointer value by 1. So the first time next is called, pointer is incremented by 1. From -1 plus 1, we get 0. And so that will access, if we use that to index into list, that will access the first value in the list. We can just return self.list index at self.pointer. In order to implement hasNext, which is checking to see whether or not there is a next value, once self.pointer reaches the last index of the list, that means there's no longer any values left. So we can do this check. Return self.pointer before the last index. Self.pointer plus 1 should be less than the length of the list. And we can run that. It looks good. Let's talk about the running time and the space complexity of this solution. So in the initialization, we do a recursive in-order traversal in order to convert the binary search tree to a list. So that takes O of n. It also takes specifically to store this list. That takes O of n space. When we do call the next function, we can get constant access to each element in the list. So that's O of 1, and this hasNext check is also O of 1, and both of these functions don't require any additional space. The solution to iterating through a binary search tree and using at most O of h space, where h is the height of this binary tree, we want to use a type of data structure called a stack. And stacks are last in, first out. So we're gonna keep a stack. We're gonna take the root node, add it to the stack, and then take its left element and add it to the stack. And we're gonna keep on adding each of these nodes to the stack as long as they have a left node. So we're going to add 2 to the stack and 1 to the stack. And so 1 doesn't have a left node. So we start popping elements off of the stack and returning them. So we pop 1 off of the stack, we return 1, and as we're popping off each of these elements, we check to see if it has a right node. And if it has a right node, that right node is added to the stack. But 1 doesn't have a right node. So we pop another element off of the stack, 2. And 2 also doesn't have a right node. We pop 3 off of the stack. And 3 does have a right node. So we add that right node to the stack. We pop 4 off of the stack. And we check to see if 4 has a right node. It doesn't. So we pop 5 off of the stack. And 5 does have a right node, 6. So we add 6 to the stack. We pop 6 off of the stack. And we check to see if it has a right node. And it does. So we add, oh, it was popped off of the stack. And we check to see if it has a right node, and it does. And that right node is 8. So we add 8 to the stack. 8 has a left node, 7. So we add 7 to the stack. And 7 doesn't have a left node, so we can pop an element off of the stack and return it. And then we pop another element off of the stack, 8. And we return that. And 8 does have a right node, so 9 is also added to the stack, and that would be the last value that's popped from the stack. And so by using the stack, we're able to return all the values of the binary search tree in order. Now I'm going to code up the iterative solution. So the values we want to keep track of in the init, we're going to have the stack, which is a list, and I'm also going to keep a pointer, which starts out at the root. And so as long as there's something in the stack, or the current pointer is pointing at something, then we should add the current pointer to the stack. So self.stack append self.pointer. We want to deal with the left nodes first. So we move the pointer to the left. Okay. And so this inner while loop will take the pointer until it gets to the leftmost node. And then we can start popping from the stack. So we set the current pointer to the top element of the stack. So we do a stack.pop, and we want to get the value of that node. So self.pointer.val. And then we want to move the pointer over to the right node of the current pointer. So we can return val. The has next here, we would just have to check whether self.stack or self.pointer, which is the same condition as this outer while loop here. So we can run our code. So I have a typo up here. Pointer. Okay, let's try again. All right, so that ran, and the answer looks good, and we can submit. And we're accepted.